No, perdón. Sí. Hola, buenos días. Eh, Gracias por estar aquí. Bienvenidos al Seminario Institucional. El día de hoy es el turno de la doctora Jennifer Close y voy a dar una pequeña semblanza de su trayectoria. Hizo sus estudios de licenciatura en el Institute for Geoscience de Johannes Gutenberg University, y su tesis de licenciatura fue relacionada a la investigación de espeleotemas enfocada en isótopos estables. La maestría la realizó en el Institute for Geoscience en Johannes Gutenberg University en Mainz, donde también hizo su maestría en investigación de espeleotemas enfocado a isótopos estables y datación uranio-torio. Su doctorado lo realizó en el Institute for Geoscience en Johannes Gutenberg University Mainz, y su tesis se enfocó en la investigación de espeleotemas, análisis multiproxy y dataciones uranio-torio. Realizó una estancia postdoctoral en Institute for Geoscience, Johannes Gutenberg University, su proyecto se enfocó en ablación láser y uranio-torio, dataciones de uranio-torio. Actualmente es investigadora postdoctoral del Instituto de Geociencias aquí en Juriquilla, y su investigación se enfoca en ablación láser y dataciones uranio-plomo en espeleotemas. Y pues bueno, los dejo con la doctora.
Thank you very much for this nice introduction and a welcome from me as well, everybody. I primarily want to talk about the things I did in my PhD thesis today, especially about the things published in a paper titled Central European Warm Phases, recorded by episodic speleothem growth during MI3. But I will also talk a little bit more at the end about some work in progress, and at the very end, of course, what I'm doing here. So in the beginning, let's just jump right into a little bit of background information so we get everybody on the same page. So I'm sure most of you are aware, but what are marine isotope stages? Marine isotope stages are alternating warm and cold periods in the Earth paleoclimate based on oxygen isotope data derived from marine sediment cores. You can see here the delta 18O against the H in 1,000 kiloyears from the Lisecki and Ramos stack, which is like a very famously known stack that is used for that. And you can see very nicely the alternating warm and cold periods. Generally, you can say that warm periods always are indicated by an uneven number, like M-1, M-5e, and cold periods usually by an even number, like M-2 or 4. My project was focused on marine isotope stage 3. And just based on what I just said, you could assume that MI3 has an uneven number, so it should have been like a warm phase, which if you compare it to, as I mentioned, stage 1 or stage 5e, which were clearly warm, it is not really that warm. But that's not the only thing that is very interesting about the stage. But what is really fascinating about the stage is something we see only when we zoom in a little bit. So yeah, marine isotope stage 3, roughly 60 to 27,000 years ago. You can see here the North Grip ice core, like North Greenland ice core record. And you can see indicated in yellow, you can see several events which are called Dansgaard-Oeschger events. Those are rapid warmings that were followed by gradual cooling. We have several of those during MI3, 17 to 3. And you can see very nicely like the rapid increase in temperature and then the gradual cooling. Those events were first discovered in those Greenland ice cores, and they're used very often to study those. The only issue maybe with those Greenland ice cores is that they have a very large uncertainty. For example, the O event, or Greenland interstadial, as they're called in the ice cores, the first one we have in stage 3, GI7. So this one here has an age uncertainty of 2,500 years. So you can really take this tiny event here and shift it for like more than 2,000 years. So if we want to talk about like the timing of these events, it gets a bit tricky when we want to use ice cores. And also in general speaking, these events are like they're studied, but the origin is still like an ongoing discussion. So we don't know too much about them. But yeah, especially like the timing is a bit tricky when we use ice cores. So an archive that would be very great to study events like this can be dated very precisely. would be speleothems. And this is what I used in my project. So let's jump into another basic or like some background information about speleothem formation. This figure here illustrates very nicely how speleothems are formed. We have the precipitation that here seeps through the soil and due the tall PC2, which is higher in the soil than in the atmosphere due to microbial activity in the soil and with respiration, it leads to this formation of carbonic acid. This acid then seeps further to the soil and the host rock and dissolves the carbonate host rock. And then further, the solution gets saturated with respect to calcium carbonate. At some point, it reaches the cave. CO2 degasses, again, to a gradient in the PCO2 between the cave atmosphere and the solution. And finally, calcium carbonate and speleothems are precipitated, and it results in the growth of speleothems, like stalactites, stalagmites, curtains, flowstones, like there's a variety of things you can find in these caves. And what we usually use are stalagmites. We use them because we have a very clear growth structure. They grow from the cave floor towards the cave ceiling. So we know this part down here at the bottom is always the oldest. And we have this very clear growth structure with, if you're lucky, nice growth bands consisting of cleaned calcite, and it gets younger towards the top. So that is very nice to work with. Sometimes you even have like a very clearly indicated growth stop or hiatus. You can then identify by like a dirt layer or like clay minerals accumulating on top. That actually is, but not the kind of speleothem I've worked with, and I work with flowstones, which have basically all the advantages of stalagmites. They form similarly, so they grow from the cave floor towards the cave ceiling. So we have the same nice growth structure. But they do not grow from a single drop of water like the stalagmites here, but from, and that's why they're called flowstones, from like a flowing body of water. And that usually leads to, like if you go to a cave and you see like large structures of a speleothem, that might be a flowstone because they tend to be like very large. Unfortunately, they also tend to form, you can see it if you compare the growth layers here, they tend to form more like thinner growth layers and grow more episodically. So that might be a bit of a disadvantage, but yeah, except for that, there is similarly nice to work with as stalagmites. And yeah, as I said, like one big advantage, or if you ask me, the biggest advantage we have when we use speleothems or stalagmites, flowstones, for climate science is that we can date them very, very precisely. The method I used is the 230 thorium uranium disequilibrium dating method. There's a dating method that can only be used for samples that are at maximum 600,000 years. After that, we have to use another method. But for everything younger, so for MI3 samples that I had, this method works great. And it is based on the radioactive decay of 238 uranium and its decay products. You can see the relevant bit of the decay chain indicated there. So we have the 238 uranium, it decays to 234 and 234 protactinium, which both have a very short half-life. So we just ignore them. We don't care about them. They don't matter in this decay scheme. We then have the 234 uranium with a significant long half-life, and the 230 thorium, which also has quite a half-life. So those three isotopes are the ones we're interested in. We have to measure when we do uranium-thorium dating. Keep in mind, 230 thorium is not a stable isotope, so it has a half-life. It will further decay. This is not the end of the decay chain. It's just that only this part is relevant if we do uranium-thorium dating. And this method is based on several assumptions. And the big one is that only uranium is water soluble. Thorium is highly particle reactive, so it sticks to clay minerals and like dirt particles and get not dissolved in the drip water. So we assume that only uranium is dissolved in the drip water and finally gets incorporated. It tells me the battery is running low. Not sure if it's okay. Should I just keep going? Okay. Okay. So yeah, we assume only uranium gets incorporated in the speleothem. And at the time of speleothem formation, so time 0, the ratio of the 230 thorium and the 238 uranium, so the radiogenic daughter and the mother, radioactive mother, is 0. And we assume that the only thorium we have in our speleothem is derived from radioactive decay. So that's the very basic assumption. We also, of course, assume we have a closed system, so we don't lose or gain any of our parent or daughter isotopes after speleothem formation, and we have no detrital isotopes. Unfortunately, we're dealing with a natural system, so those assumptions are never fully met. And in my case, especially the detrital contamination of thorium was an issue. And that is, in fact, something we always correct. And to do this, because we then have some thorium that is not part of our decay of our decay chain, we obviously have to correct for it, but we cannot deduce like how much of it is actually radiogenic, which is part of the detrital material. So we use the 232 thorium as an indicator for detrital contamination. So another thorium isotope that is not part of our original decay chain. And so we measured this one as well. We then usually use a mean global correction factor based on the Earth crust ratio of these two isotopes, and we apply it on all samples. You can calculate an individual correction factor, which is actually what I do, but the standard approach is just use this global correction factor. And of course, the effect of the detrital correction increases alongside the level of contamination. And it's cut off here. I don't know why. And so if you have like a very clean sample, there's no detrital contamination in your sample, you don't have to worry. You probably don't even notice this correction. If you have detrital contamination in your sample, it might increase the uncertainty of your ages quite significantly. So the general rule of thumb is just avoid it. Like if you have a sample and you see detrital layer, you know there's like just stay away from it. Get as close as possible because you want to resolve like when this growth stop might have happened, but try like be as cautious like as possible and try to not incorporate it in your sample, which sometimes is a bit tricky to do, as you will see further on. Okay, so we have all the basic information. We know about marine isotope stage 3 and Dansgaard-Oeschger events in theory are like a very interesting topic to study. We know speleothems would be a great opportunity to do that, but what was the actual idea of my PhD project? So on this map, you can see Europe a bit zoomed in, and you can see all the dots indicating MI3 records. We have some marine records in blue, some terrestrial records here. This one from Germany is a very nice pollen record that we have, but unfortunately, because it cannot be dated individually, it was tuned to the North Greenland ice core. So we have the same issue with this record as well with the ice cores that we don't have. Like we have the same issue with like the timing of the events. And in this greenish color, we have several speleothem records. And if you look at the distribution of those records, you could tell like they're mostly from more southern Europe, maybe more coastal regions. So generally speaking, like warmer regions in Europe. We have some from the Alpine region here where they grew from glacial meltwater. We have one here that's actually Spunka Cave, which was a record one of my colleagues in my working group worked on. But have like very, very short growth phases and not very, very long during MI3. So we can really say like Central Europe, there's nothing there. So the assumption very, very long was that MI3 in Central Europe was too cold and too dry to enable speleothem growth in general, because we need this liquid water, we need this little bit of vegetation and salt on top of the cave. We saw MI3 was not that warm, so it was just assumed like this warm events never reached Central Europe, or not at least enough to enable speleothem growth there. However, this is one of the samples my supervisor had before we started working on my PhD project and to write it. And this is a flowstone titled BB9, and it's from this cave here, which is called Blesberg Cave in Germany here. And it's clearly more Central European than all of the other records. And so we took everything I already told you. We have MI3, we have those short-term Dansgaard-Oeschger events with those rapid warming and the gradual cooling. We have a flowstone sample, which shows like this part down here was MI3 we knew from some previous dates or previous ages. We knew those flowstone samples tend to grow more episodically. And if we look at our sample, we can see those whitish layers, which are our growth layers, and those brown dark layers, which are the layers I told you to stay away from if you do uranium thorium dating, because they're like contain like clay minerals, like the dirty particles, so indicated growth stop. So we took all of that together and we looked at the sample and we thought like, how nice it would be if we could like very precisely date the sample, because we assumed that all of those individual growth layers would represent an individual DO event. So then we would have like an absolutely dated, independent from the growth from the ice cores. So we don't need to tune anything. We can date our sample itself. We can date them precisely. We do a multi-proxy approach, and then we have a very nice record from Central Europe, which is something we do not have yet. So that was the idea for my project, and we thought very nice, very straightforward. There should not be any issues. In the end, I worked with 3 flow stones, BB9, BB10, and BB15. All had growth phases during MI3, obviously, indicated in red here. Not sure where sometimes it's pushing it out of my boxes. And yeah, those were the 3 samples I worked with. And in the beginning, of course, I started with dating the samples. And the first step you usually do if you do uranium thorium dating, at least in our lab, which is actually, I took the pictures like from the homepage of my old university, so all the labs. I will show you other labs I worked in. And the first step I like to do is like I took a handheld drill. Some people like to use a tiny saw, like a saw to cut tiny pieces out of the sample. And yeah, as a first step, like you get your sample material to do uranium thorium dating in the lab. In this case, the sampling precision of the drill I used was 1 millimeter. And I will always show you like how they look on the sample. As I said, like this right here, like this part is 2.3 centimeters. And some of these layers are not even 2 millimeters thick. So have that in mind when I tell you, like show you the precision and what I'm trying to avoid, which is these brown layers, because that is what we are trying to do. So I have a sampling precision of 1 millimeter plus me doing it manually. So you can probably add a little bit of uncertainty. So it was a bit tricky to avoid these detrital layers. Then this method is solution-based. So it's like the very standard approach. You take your sample, bring it to the chemistry lab, you do uranium thorium separation, column chemistry. So you have, at the end, you have 1 beaker with uranium, 1 beaker with thorium. You take it to your multi-collector lab. We have the Neptune Plus. It's the same multi-collector we also have at the Institute here. And you have another 3 days of measurement. So in total, it's like 7 days of lab work. When you have the lab just for your own, probably takes up to a few weeks to finally get your ages. You will always get 7 ages in like 1 run. But if you manage to do all of that, you have a very, very high analytical precision. So the ages, generally, if everything goes great, are very high precision. However, as I said, it is very hard to avoid this detrital contamination. And in the end, for my sample here, I ended up with only 7 ages I could use. Other samples were just not usable. And yeah, so the next step was like, okay, I have to get like a higher precision in terms of the sampling. So I used this device, which is a micromil, which is the device we would usually use to sample for stable isotopes. The sampling precision is higher, like 300 to 500 micrometers, depending on the drill bit you put in here. It has a microscope on top, and then you have the software where you can see through the microscope and decide where you want to drill. It's a computer-driven drill, so the sampling precision is a lot higher. And then the entire procedure, like the chemistry and the measurement, is exactly the same. So it's the same time consuming, it's the same level of expensive, because those methods tend to cost quite a bit of money. But the same high, like very high analytical precision, and a bit easier to avoid this detrital contamination. And I ended up with 15 ages I could use. And when I say could use, it does not mean it's the most precise ages you could ever have. There were ages that were not completely awful. There were a few that were very, very great, like very high precision, but not all of them were usable. And the problem, or like the issue we ran into, is that we had to decide, because we wanted to do like a precisely dated sample and then do a multi-proxy approach. So what we have to do is like we have to do like H models. And for an H model for each growth layer, so we can plot our proxies then against H, we need the minimum of 3 very good ages. So that's the minimum you should like go for. And that was just not the case here. So we had to decide, do we scratch the first idea that we get like great age models for all the growth layers and just give up basically, or if we try something else. And we did try something else. And so in the next step, I decided to use laser ablation, which is a step away from the very standard approach, less like standard approach. Like you usually don't use the micromill, but this is really not standard uranium thorium dating. So it was a bit like, it's not completely unheard of, but it's not that often done. So what you do, you put your samples in your laser chamber. You have a much higher sampling precision, 2 times 150 micrometers. This is the spot size we used, and 2 times because we had to do 2 parallel line scans next to each other. Like those orange dots will always be 2 line scans because our mass spectrometer did not have we could not measure uranium thorium at the same time, so we had to do 2 parallel scans. It is an in situ technique. As I said, you just put your samples in a laser chamber, throw it in a laser, and just measure it. So much faster, less destructive, and so much cheaper. And just in comparison, several weeks for 7 ages, and like hundreds and hundreds and thousands of euros against like 1 day of work for like 60, 70, 80 ages per day, and like a few €100. So it is much faster, much cheaper, less destructive. However, we lose the high analytical precision because we're just very limited with the sample amount we can ablate out of the sample. And we just run into the issue of counting statistics. However, very easy to avoid tetraethyl contamination because it's a laser and it's much more precise. So I ended up with 19 ages from that. And then I took it one step further and did another approach with the laser, but this time not parallel to the growth layers, but as a transect. So just across all the growth layers. Across the layers, the growth stops, everything. Everything basically is the same here. It's the same precision, the same, like in terms of sampling and analytical precision. However, now I had a continuous line of age data information, basically. And what I did is that I calculated the ages incrementally from that. And I decided to use a 0.2 millimeter resolution for that. So I ended up with 82 ages just for this 2.3 millimeter section of sample. So in the end, I had more than 100 ages for this sample and more than 500 ages in total, which is for those for you who never did any dating, like uranium thorium, uranium lead, like not uranium lead if you do laser, but like in general, if you do uranium thorium with spelothems, that is a crazy amount of ages. That is not the normal amount of ages you have. But yeah, we were happy with that. We had our ages, quite a lot of them. So next step was to calculate age models. So yeah, as I said, a few precise solution ages, many more less precise in terms of analytical precision, laser ablation ages. And then we ran into another issue because conventionally used methods for age depth modeling, like CoPROS, DAL-H, they're designed for ages with a spatial resolution of a few millimeters to a few centimeters. Not the case here. Comparable age uncertainty, not the case here. And a limited number of age inversions, which is definitely not the case here. So the age models I tried to use, they just gave up. They couldn't handle it. Like they either crashed, they kept calculating and never produced an age model, or they just gave an age model that was complete nonsense. So we just could not use that. So we had like a set of ages that looked like this, which I admit looks like a cloud of of ages. And we had to figure out now how to use it in a way we wanted to. In this figure, you can see against the age in kilo years, the distance from top. It's one of my BB9 growth layers. You can see it's not like it's in centimeter scale. It's not a very thick growth layers. We somehow managed to have 4 precise ages in those green colors. The micromilled ones are the light green. And we have the laser ages in black. These are the ones parallel to the growth layer. And these are the calculated ones. That's where there are so many. And you can see it's a mess. It's like a cloud of ages. And like, yeah, it's a mess. And it's a cloud of ages. So what you can also see is that there is an age model here. So how did we do this? And we used something called the York fit. It was published by York et al. In 2004. It also has an implementation in I think the isoplot R package in R. And what it is like an arrow-weighted linear regression. And we modified it to fit our needs. And what this fit does, it weights precise ages more strongly, which is great because we wanted to use our precise ages as anchor points and just support it with our laser ablation ages. And it also accounts for uncertainties in both X and Y direction. So in the uncertainty for the age and also for the sampling, which was also quite different for all the samples we had. I then ran 10,000 Monte Carlo simulations each, and the result of this York fit then gave you the parameters of the slope. So basically like the growth, I forgot the word, like like how fast the speleothem was growing, and the maximum and minimum intercept, so the end and the beginning of my growth, of my age models. And of course, what we had to do was exclude simulation with a negative slope, because a negative slope would mean the speleothem had negative growth, which obviously does not make sense. And especially for those like thinner growth layers, that meant to exclude quite a lot of age models, actually. Sometimes I only could use 6% of those 10,000 Monte Carlo simulations. So sometimes it still was a bit tricky. However, with the results, it was then calculated a mean age model, the one in red here, the corresponding confidence limits in gray, and the probability distributions or histogram of the simulated age data. Because that is what I decided to use first, not for plotting proxy data. Of course, I need an accurate age model for that, but to see how it fits with our DO events, which was our first initial goal. I used those probability distributions. And this looks like this. On this figure, you can see up here again the Northrop ice core against age of kiloyears. And then you have the age distributions as histograms from BB9, BB10, and BB15. And the numbers always correspond to the growth layer. And what it shows, it visualizes the probability of the age ranges of the individual growth phases. So what does it mean? I had 10,000 Monte Carlo simulations, and we used like the precise ages were used at those anchor points. So of course, and it was like weighted more strongly by the fit. So if I had like a precise age, obviously the age model, it was more often included in those age models. So it will show up in this distribution of this histograms more often and will help us like to, be this top point here. So it really is like the distribution of ages that resulted from all the 10,000 Monte Carlo simulations, from all my age models. And to better compare it, like all those histograms have the same amount of bins. And that's why the width of the individual bins and the histograms reflects the precision of the age model. And less precise age models reside in wider histograms. So you can say like, these turned out pretty well. This one, not so much. And still, we could use that now to see that most histograms can be assigned a specific DO event or green interstadial indicated in gray. You can see most of them fit within one of these events, which is what we wanted to do. We're happy with that. But we had to admit this, displaying the ages like this, it is not very handy. It's like you don't look at this and be like, yeah, of course, I know what that means. So what I decided to do is combine all of that. I took all my age models of all my growth phases, of all my samples together, and did a combined growth history as a frequency curve. I used the frequency analysis and the origin software, and it gave me this up here again, the North Korean ice core in gray, the DO events, and now I have a basically composite record of speleothem growth. And what was nice, because it reduced the impact of the less well-constrained growth phases, like those white histograms you saw, they don't have much impact here. It also shows us that if you look at the early stages of MI3, we see more frequent and more prolonged growth phases in early MI3 in comparison to mid or late MI3. And we can also see that the growth phases we have often lack the onset of the DO event we see in the Greenland ice cores. So we can get a climatic information just of our growth phases without doing any proxy analysis at this point. And we were quite happy with that. So yeah, that is how we combined all the staging approaches together and ended with this. So to just summarize this first part, Speleothem growth requires both liquid water and vegetation above the cave. That's the basic requirements we have for speleothem growth. Flowstone growth was inhibited during cold stadia periods. Like if it was too cold, there was no speleothem growth, or too dry. It also means that those flowstones represent the periods during which the climate in Central Europe was favorable for speleothem growth, and this can be considered warm and humid climate. Potential permafrost above the cave has to be melted. And I didn't show it, but we actually have evidence for permafrost in Germany during this time period. Not in my cave, but we have some cryogenic calcites from other caves. So there is evidence for permafrost conditions during MI3 in Germany. So if we had those, that must melt, of course. Otherwise, liquid water would never reach the cave. We also need soil cover and vegetation, and this need to have time to reestablish. At the onset of the DO event, therefore, the initiation of the speleothem growth we see will be delayed. We have the buffering effect of the karst above the cave. We have the time that is required for permafrost thawing and the vegetation to redevelop. So it makes sense that the lag we saw stems from exactly those buffering effects, if you want. And this all results in flowstone phases, which represent the minimum duration of warm climate in Central Europe during MI3. So it's it's important. It's like the minimum duration. It's like we have probably time where it was warm in Central Europe, but it did not reach the cave. Probably our speleothem stopped growing before it was not the climate conditions were like horrible again. So it is the minimum duration we see, and we believe that can be considered the peak warmings we have. So really the warmest phases during MI3 or the specific DO event in Central Europe. And that's then what we titled Central European warm phases. So as I said, we also did a little bit of proxy analysis. So now we're jumping in the work in progress part that is not published. It should be published, but it's not. So let's look a little bit more in like what the climate in Central Europe actually looks like based on actual climate proxies, not just our growth phases. So you can see again on top, the North Group ice core, the gray bars indicating the DO events. At the bottom, we have a pollen record from Western Germany, the one that's tuned to the North Group ice core. And we have several of my proxies I measured. We have stable isotopes up here, oxygen and carbon. We have 3 trace elements, barium, magnesium, and strontium. We have calcium isotopes here, and we have strontium isotopes down here. And I want to talk about those 4, because we find them the most, like the clearest to interpret. And also we decided if we look at the overall trend of MI3, like what we see here, because we have the from 60 to 30,000 years, we just will look at the overall trend and not every up and down of every growth phase, because they sometimes are just too short to work with. So if you look at the delta 13C, we have a trend towards more positive values. So the axis is inverted, and actually some of these axes are inverted. So we have a trend towards more positive values. Very clearly, and we want to use it, or we think we can use it as a microbial activity, like in soil microbial activity proxy. So the trend towards more positive values would indicate reduced soil CO2, less dense vegetation, and colder and drier climate conditions, which actually makes sense when we look at the pollen record we have here, because those are grass pollen. And these are the tree pollen. And you can see the trees stopped growing at the later phases of MI3. Especially this one here is a tree that really needs the warm climate. So it makes sense that we see this declining trend also in all our records. Then we have the barium trace elements. We think we can use as a soil leaching indicator. We also have the host rock, the modern host rock measured here. And we see a trend somewhat towards this host rock level, especially in this early phases here. And then it doesn't change that much, but it gets closer to the host rock level. So we would assume less leaching from soil. We also did a soil analysis, so we know most of the barium stems from the soil. And it will also indicate drier conditions, which again fits very nicely. Then we have the calcium isotopes here, which show it a trend towards more positive values as well. And this proxy is not commonly used in speleothems, but sometimes used as an indicator for precipitation or prior calcite precipitation, which means the calcite, it's precipitated before it reaches the cave. And that usually indicates less rain, less precipitation, drier climate conditions. So again, we have this trend towards drier climate conditions, which again fits very nicely with our other proxies. And lastly, we have the strontium isotopes. We also measured the host rock here, and it can really be used like as an indicator from like, is it a solid signal or is it like a host rock signal? And we have the trend again to host rock signal, which might indicate longer residence time in the karst above the cave, less precipitation, more prior calcite precipitation. So those proxies fit very nicely with like the overall idea we also saw in the growth phases already, that we can say that the overall progression of the climate in MI3 was declining. It was getting from warmer, more prolonged growth phases to drier and colder climate conditions, which again fits nicely with this pollen record. But unfortunately, because we only looked at the overall trend, so we also wanted to look into something a bit more in depth. And that is the DO14, which is, as you can see, the longest DO event we have during MI3. And it also is the longest growth phase we have in our record. And here you can see basically the same, basically the same proxies before. We have the north grip up here, like shortened to fit. It's not the entire Greenland interstadial DO event 14. It fits our growth phase. But yeah, we have the Greenland the north grip up here. We have a protactinium thorium proxy or record here, which indicates a stronger or weaker AMOC. Then we have our stable isotopes, so the same trace elements as before, and the calcium isotopes. And what you can see when you look at the Greenland interstadial in the north grip, that it is two-phase. So we have one phase here and one phase here, which is divided by this cold phase, which is also described in the ice core. It's just a GI14b, which you can see very nicely here. And you can see this two-phase structure also in our record. You can see it very clearly in our calcium isotopes. You can see it maybe in our strontium concentration. I had discussions that you might see it in the stable isotopes, but I would say you cannot. But yeah, if you want to, maybe you can see the stable isotopes. What you can also see, speaking of stable isotopes, is those stable isotopes look extremely similar. Like sometimes I was unsure if I really plotted two different stable isotope records here because they're so extremely similar. So we, of course, would assume one dominant factor influence on those two stable isotopes. And as delta 18O tends to be a bit more complicated to interpret, there can be different factors. We stay with the delta 13C as an indicator for microbial activity. And yeah, we just say like the influences we have there must have been like very similar. What is very nice when you look at the stable isotopes, though, is that you can see this basically this initiation phase, at least that's what we believe you can see here. That is similar to this general lag we see in our records, but that we also see in our proxies. So we go from less microbial activity, so drier condition, less dense vegetation, and things like that, to more vegetation, more microbial activity. We saw it also in the delta 18O. And that we really have like this start of the warm phase in our record, which I think is very nice. You can also see very clearly those cold events, by the way, in both our stable isotopes. Then, as I said before, we did a soil analysis. So we have barium and magnesium we know is predominantly from our soil. So we can also see that the barium reaches the host rock concentration here in the beginning of the phase, which again fits very nicely with the idea that we have this initiation phase of reestablishment of the soil and vegetation above the cave. And also the magnesium is very low here, the axis again inverted. We can see the same, like we also like a drip or like a drop in the barium concentration here in our cold phase, which makes sense when we use it as a soil leaching indicator, because it might be like reduced soil CO2, like the leaching potential was just lowered to cold stress, dry stress, something like this. So I think it's very nice that we see it here as well. We don't see it in the magnesium. Please don't ask me why. Because we don't know. The magnesium very often does interesting things. We also see from the soil analysis the strontium is very easily leached from soil with a weak acid. This is also very, like at the lowest value in the beginning of the phase, which fits again with all our proxies, and then steadily increases, which makes sense that we maybe have like a warming progression for this event, with the exception of this cold event here again, which makes sense because as it's a cold event. So we believe we can use the strontium as a proxy for soil activity. Then we have our calcium isotopes that show more precipitation with like ongoing time of the DL event. And then we say drastic drop after the cold phase. We unfortunately don't have the resolution to know what is happening in this cold phase here, so we cannot say anything about this. But yeah, we see this drastic drop. And then we also see that our growth phase stops. And even though we see the same drop in the AMOC, that is like very weak here, we see that AMOC here recovers again, but our system did not. So even like the general system, like the Greenland interstadial, the DL event kept going, it was just not warm enough, or like not strong enough to reach Central Europe maybe, or like just not our cave. So yeah, the system we see did not recover again. So to conclude this PhD project, the blast-back flowstones offer a great opportunity to investigate the past climate variability of MI3 in Central Europe, which is something we did not have before. So that's a very nice thing, I think. We see that MI3 in Central Europe was warm enough to enable speleothem growth, because if you remember in the beginning, I showed you that there were no records from this time period in Central Europe, and the assumption was it was too cold, too dry, it was just not possible. So just the existence of our record shows that that is not the case. We see that the record is highly sensitive to environmental changes and represents the peak warmings during the last glacial period in Central Europe. We see that the growth phases very often lag the DO events, as we see them in Greenland that are shorter, especially in the middle and later phases of MI3. They on average then only cover 25% anymore. And we see an overall trend from humid climate during early MI3 towards dry and colder conditions with the progression of MI3, which fits nicely with other records and makes a lot of sense. But yeah, it's the first time we see it actually with a nice record in Central Europe, or like a good dated record. We have DO14, which was a particularly warm phase, and we see it also was like that in continental Europe, and it vitally influenced the vegetation moisture availability over the continent. We have two distinct short-term cold events. I only talked about one, like GI14b, which has not been shown in any other terrestrial records I know of before. Or maybe it was there, but it has not been discussed. We actually checked, and we see it in the Bunker Cave record, but yeah, it was not discussed. So that we see it in our record, again, is very cool, I think. And generally, it allows a first-time high-resolution, in-depth look into those short-term climate events. Okay, so that was the PhD project. So let's have like 5 minutes left. So let's briefly talk about what am I doing here? Because it's not uranium thorium dating. Even though the title of the project we have, which is high resolution uranium thorium and uranium lead geochronology of spelothems from northwestern Mexico to constrain the evolution of the North American monsoon during early and mid Pleistocene. So this one has uranium thorium, but we really focus on the uranium lead here. And like the overall projective is to do exactly that. Climate reconstruction, early mid Pleistocene using Northern Mexican speleothems to reconstruct the North American monsoon. But as we saw, like the basis of those reconstructions heavily rely on the dating part. So prior to any proxy analysis, we have to do the dating. And so the dating part is the main objective of this project. And it is to establish laser ablation uranium lead dating for speleothems at the Institute, because we don't have that here. So yeah, the idea is to establish the method based on the experience that it is at the Institute of Uranium Lead dating of zircons, because that has been done for quite a while, and has a lab specially designed for that, and has a nice existing laboratory setup, and combine it with my experience of dating speleothems and doing laser ablation, not uranium lead, but uranium thorium. So basically what I was doing in my PhD was this, like uranium thorium with the laser, which is suited for samples not older than 600,000 years. And very simplified, what I'm doing now is this, As I said, like there was not the end member of this decay chain. It's a 206 lead, which is suited especially for samples that are older than 600,000 years. And if we are a bit more precise, that is what this entire decay or like the dating method looks like. I will not talk through all of that. Just that lead has 4 naturally occurring stable isotopes, the 204, 206, 207, 208. And it has like a basis of the 3-couple geochronometer. We usually use a combination of these two decay chains. So the 238 uranium, which decays to 206 lead, and the 235 uranium, which decays to 207. And they're usually combined to improve the accuracy and like is a great method to use. There are people or like studies who use this decay scheme chain as well. There's the thorium series, and it starts with 232 thorium and ends with the 2 or 8 lead. And if you take anything from this talk today, it is that initial thorium in speleothems is usually not our friend. So we don't use this and we don't need this in this project. So yeah, that is the basic idea and what I'm doing. So how's it going? Generally, not bad, I'd say. We had in the beginning what you do to establish a method. We like had several test runs to establish the best laser parameters and work on the general precision. It's like a work in progress. We tweaked around a few parameters. I will not show you everything I did because it's, yeah, it would be a lot. But yeah, so we figured out what to do best. So can we precisely date all carbonate samples yet? No, unfortunately, we cannot. But can we precisely date some of the samples or somewhat precisely? Yes, we can. And these are some results from my latest experiment. And what I did is that I used calcite or carbonate reference materials. So it's the material we want to work with, but they have a known age. So we actually know what we are looking for. In the figure here, you can see the terrum, which is like a big calcite crystal reference material we have, which is an accepted published age of 208.5 plus minus 0.06 million years. And we got an age of 209.4 plus minus 8.8 million years. So if you just look at the age, like what we dated and what we are looking for is not too far off. It doesn't look too bad, if you ask me. The uncertainty is too large, so we definitely have to work on that. So that is a work in progress thing. The initial plan was to use the multi-collector we have here, so the Neptune Plus, the same one I used in my PhD, but it has been broken, unfortunately, so fingers crossed it will be fixed soon. And then I hope it will fix or might fix the problem of the uncertainty because it has I believe 30 times higher sensitivity than the machine I use right now. Then we have another one here, which is the RA138, which is a published age of 321.99 plus minus 0.65 million years. And what we have, or what we dated the last time, of 319.5 plus minus 4.7 million years. So again, the general age is there, especially within the age uncertainty. Again, the age uncertainty itself is too large, but yeah, we can date those samples. However, we have a problem child that's called SB19, which is a stalagmite reference material, which has a much, much younger age of only around like 1 million years. It's very precisely dated, has an uncertainty of 0.024 million years. And it's specifically designed to, or it's not designed, but it's published as a reference material that can be used to date, to correct young samples. So how's it going with this one? Not as good, I would say. So it's from the same experiment. I used 2 different reference materials to correct them. And one time we're a bit too young. The other time we're almost double the age. So we have a delimitation here. So we cannot date very, very young samples yet. So the current limit of the method is somewhere between 200 million years and 1 million years, which is a bit of a range. So we have to figure out where exactly this range is and what we can like date and be sure that it is correct. I have a sample on my desk right now that is around 40 million years. So the next step will be to date unknown samples where we have like a range, so we more or less know what we are looking for. And yeah, we will try to get closer to those 1 million years old samples. So we hopefully can date all of the uranium-lead range speleothem samples we want to, and have this method established at the Institute, which would be very nice. And yeah, that was my last slide. My pointer's not working anymore. No, it is. Oh well, I'll click too much. So yeah, I want to thank everybody that is shown on these pictures because they either contributed to a PhD project or my current project, all those institutions that helped me, working on all of those projects. And yeah, thank all of you for your attention.
Muchas gracias, doctora Jenny. ¿Alguien tiene una pregunta?
But in English, please. Please.
English or Spanish?
Please, if you want to answer.
Yes. So when you mean that you have warm and humid periods in Central Europe, do you have any idea of how warm are you?
I would love
like
to.
Today, like day, 30°C, or it's just more humid, warmer than.
I tried. We did TIX 86 temperature reconstructions, and they did not work out. It was like we were at the limit of the method, so we tried to get a temperature reconstruction going. It did not work out, so I cannot say it. I don't think I brought it, but I measured fluid inclusions and I measured fluid inclusion temperatures, which are tricky, right? They're not, and I have to remember, like they were, let's say surprisingly warm. I will not give you like a range or something, but it was surprisingly warm for the MI3. I can look up the exact temperatures. I don't know them from the back of my head because then I was told we don't use them because they're too unsure to use as a proxy. But I know from another study where they used it's an archaeological paper, and I think they used some horse teeth from this time period, and they did some temperature reconstructions, and I believe they almost said they reached like Holocene temperatures, which I find very surprising at some points, but I would have to look it up again. Yeah. But yeah.
Because those are also the earliest human settlements.
I know. It is. I know. We were thinking about if we somehow could put that in the paper, because it would be very nice to have like a change of like Neanderthals and like early humans. And Hubert von Hoff, he desperately wants to do this. My supervisor desperately wants to not do this. So I'm in the middle. So we're currently discussing this, and I'm not an expert on this topic, but I know that there was a discussion going on that the climate was like too harsh sometimes for the Neanderthals to they couldn't adapt to it, and that's why we have this change there. And so it's hard to say anything about how are the temperature conditions were they better fit for these or that. But I would say the study at least supports the idea that we have because I think this transition happened in the middle of MI3, if I'm not mistaken, and we see the decline of warm and humid temperatures there. So I would say my study or our study could at least support this in some way. But to say definite temperatures, yeah, I'm careful with that. I would have loved TIX 86 temperatures, and we did it at the MPIC, but they did not work out, unfortunately, because I wanted them especially for these cold phases in the GF14b, because we're still not sure if it was just how cold, is it just dry? Is it just a dry stress? Is it really cold? Because we really wanted to know this, and it's kind of hard to figure it out with our proxies. Could be both. But yeah. Sorry.
Yeah, I have a question. Do you think we'll be able to date calcite when we know the process?
I never tried I mean, In theory, do they have enough uranium? If they're calcite and they have enough uranium and they have a good age range, you could try. I mean, why? I wouldn't know why not. Luigi and Juan Pablo are both doing this, so yeah.
You can standardize outside from the process.
Yeah.
You have the standards. These standards we use to these.
Yeah, exactly. So wouldn't know why not. So we could try. I mean, as I said, like currently we have this limit where I don't know where it is exactly. And like 1 million and 200 million years. That is a range. I really hope we're closer to 1 million, obviously. But we just don't know it right now. But I mean, we can try. Sure.
Gracias por su asistencia y los esperamos en el próximo seminario.